Gravity, warping space and time. The mystery that binds the universe. 1. Hello and welcome. Hey everyone. Welcome back to Chisholm's Science Tech YouTube channel where science meets imagination. If you're fascinated by black holes, time travel, and the vastness of the cosmos, you're in the right place. Today, we're going on an epic journey to uncover one of the most mysterious and powerful forces in the universe, gravity. It's the invisible architect that shapes the cosmos, from the fall of an apple to the dance of galaxies across billions of light years. But gravity isn't just a force that pulls things down. It bends light, slows time, and curves the very fabric of reality itself. Whether you're a student, a space enthusiast, or just curious about how the universe works, I promise you, this journey will change how you see everything. So grab your space helmet, let's dive in. 2. What is gravity, really? Let's start simple. Gravity is the force of attraction between objects with mass. The more mass something has, the more gravity it exerts. We feel gravity every day. It's what makes apples fall, rain pour, and keeps oceans tethered to the earth. But what really is it? That's a question that puzzled humanity for centuries. In classical physics, gravity is just one of the four fundamental forces, the others being electromagnetism and the strong and weak nuclear forces. Yet gravity stands apart. It's the weakest, but it operates over the longest distances and affects all matter and energy. Unlike magnetism, which can repel, gravity always attracts. From ancient philosophers to Renaissance thinkers, people have tried to grasp its essence. But it wasn't until the 17th century that we began to truly quantify this strange force. 3. Newton's laws and the classical view. In the 1600s, Sir Isaac Newton revolutionized science. With his famous equation, F equals G, m1 asterisk m2, r squared, he gave us a formula to describe gravity's strength between two objects. This allowed scientists to predict how planets move, how tides flow, and how to launch objects into space. But Newton's view was mechanistic. He imagined gravity as a kind of invisible tether, a mysterious force acting across space instantly. It worked incredibly well, for everything from building bridges to calculating eclipses, but it left a big unanswered question: how does gravity actually work? What is causing this force? Newton himself admitted, "I frame no hypotheses." It would take over 200 years and a new way of thinking about space and time to get closer to the truth. 4. Einstein and the warping of spacetime. In 1915, Albert Einstein turned physics on its head with his general theory of relativity. Rather than seeing gravity as a force, Einstein proposed that mass actually warps the fabric of space and time, a radical idea that changed everything. Imagine spacetime as a flexible sheet. When a heavy object, like the sun, sits on this sheet, it causes a dip. Planets like Earth don't orbit because they're being pulled. They orbit because they're moving along the curved path created by that dip. It's like marbles circling a depression in a stretched rubber membrane. In Einstein's view, gravity isn't something objects emit. It's a property of the geometry of space-time itself. And that geometry tells matter how to move. This elegant idea explained things Newton couldn't, like the precise orbit of Mercury and the bending of starlight. 5. Space-time explained. Let's zoom in on what spacetime really means. You know the three spatial dimensions: length, width, and height. Add time as the fourth dimension, and you get the 4D continuum we call spacetime. Massive objects like stars or planets curve this 4D grid, and that curvature affects the path of anything nearby, even light. That's why light bends when it passes near a massive object, a phenomenon known as gravitational lensing. But it's not just space that curves, time does too. In regions of stronger gravity, time literally ticks more slowly. This is gravitational time dilation, and it's been experimentally confirmed by flying atomic clocks on planes and comparing them to ones on the ground. The difference is tiny, but real. 6. Experimental proofs. Einstein's ideas were bold. But bold ideas need proof. In 1919, British astronomer Arthur Eddington led an expedition to observe a solar eclipse. His goal? To measure the position of stars near the sun and see if their light had been bent by its gravity. The results matched Einstein's predictions, catapulting him to worldwide fame. Fast forward to the 21st century. In 2015, the LIGO Observatory detected gravitational waves, tiny ripples in spacetime caused by two merging black holes over 1 billion light-years away. These waves stretched and compressed space by less than a fraction of a proton's width. But the signal was clear, and the implications enormous. Spacetime isn't just a metaphor, it's real, and it can move. 7. Gravity and black holes. Black holes are the ultimate manifestation of gravity's power. Formed when massive stars collapse under their own weight, black holes compress mass into an incredibly small space, creating a point called a singularity, where density becomes infinite. Around this singularity lies the event horizon, the invisible boundary beyond which nothing, not even light, can escape. It's the ultimate one-way door. Einstein's equations predicted these monsters, but even he doubted their existence. Today, we've imaged one directly, the black hole in the galaxy M87, proving their reality beyond doubt. 8. Gravity's role in the cosmos. Gravity is the architect of the universe. It pulls clouds of gas together to ignite stars. It binds stars into galaxies, galaxies into clusters, and clusters into the cosmic web, a vast network of filaments stretching across the observable universe. It also acts like a cosmic magnifying glass. When light from a distant galaxy passes through a massive cluster, the gravity bends and amplifies it, letting us see things we otherwise couldn't. This is gravitational lensing, and it's helping us map dark matter, which exerts gravity but emits no light. 9. Gravitational time travel? If time slows down near strong gravity, could we use it to travel into the future? Surprisingly, the answer is yes. Astronauts on the International Space Station already age slightly less than we do on Earth due to both their speed and weaker gravity. But near a black hole, the effect becomes dramatic. In theory, if you orbited just outside a black hole's event horizon for a few hours, decades could pass elsewhere. This concept was explored in Interstellar, where an hour on a water-covered planet near a black hole equals 7 years outside. Based on real physics? You bet. Consultant Kip Thorne even won a Nobel Prize for his work on gravitational waves. 10. Quantum gravity and the future. Einstein's relativity explains big things: planets, stars, galaxies. But the world of the very small, described by quantum mechanics, plays by different rules. And when we try to combine the two, say, at a black hole's singularity, they clash. This is the holy grail of modern physics, a theory of quantum gravity that unites the macro and micro realms. String theory, for instance, proposes that particles are tiny vibrating strings in higher dimensions. Loopquantumgravity suggests spacetime is made of tiny loops woven into a fabric. These are just a few contenders, and the search continues, pushing the limits of human understanding. 11. Everyday effects of gravity. Believe it or not, gravity's weirdness isn't just for space nerds. It affects your GPS navigation. Satellites orbit Earth in a weaker gravitational field, so their clocks tick slightly faster. If we didn't correct for this, your phone could be off by kilometers. Engineers factor in gravity when building skyscrapers, bridges, and roller coasters. Even video game physics engines simulate gravity to make movements feel realistic. And in medicine, gravity plays a role in blood flow, muscle health, and bone density, especially in space. 12. The takeaway: gravity is more than a force. So what is gravity? It's more than a force. It's the whisper of the cosmos, the invisible architect of stars, planets, and time itself. From Newton's apple to Einstein's equations, from warping time to collapsing stars, gravity is a profound mystery that connects us to the heart of the universe. It tells us that the universe is not a static stage, but a living, breathing fabric, bending, stretching, and vibrating with every massive move. Thanks so much for watching Chishim's Science Tech YouTube channel. If this video sparked your curiosity, please give it a thumbs up, share it with your fellow science lovers, and subscribe for more epic journeys through space and time. What blows your mind most about gravity? Drop your thoughts in the comments. I read every one.